A ball rolling uphill. A bowling ball rolls without slipping up a ramp that slopes upward at an angle beta to the horizontal. Treat the ball as a uniform solid sphere, ignoring the finger holes. Part A. Draw the free body diagram for the ball. Explain why the friction force must be directed uphill. Part B. What is the acceleration of the center of mass of the ball? Part C. What minimum coefficient of static friction is needed to prevent slipping? So this is our situation. We have the center of mass in the middle. It's a uniform sphere. This is our contact point with the inclined surface, and the ball is rolling without slipping, and it's going upwards on this slope. Okay. Now, if we start with the free body diagram of the ball, we can set up our coordinate axes so that the x-axis coincides with the slope in the upward direction, y-axis is the normal direction, and z-axis is coming out of the page. And we have the weight of the ball pointing down from the center of mass, it's mg. We have the normal force from the surface. The ball is rolling uphill, so omega, this is the direction of omega, but it has to be decelerating as it goes uphill. So we need to have a torque that is going to act to decrease this omega, and that torque will be provided by a static friction that points upward in the slope. So if it were pointing downward, then it would cause an angular acceleration, so the ball would rotate with higher and higher angular speeds as it rolls up, so that doesn't make sense. So that's how we decide on the direction of the friction force. So if this angle is beta, if we draw a perpendicular to the surface here, this would be 90 degrees and 90 minus beta, you can see. So this angle that mg makes with the vertical axis here, the normal axis, would be beta. Okay, so we have determined that this angle is beta as well. All right. So let's remember what we know about rolling without slipping. So for rolling without slipping, up the ramp, we have the center of mass speed given by angular acceleration omega times the radius r, capital R, of the sphere. So the contact speed, Vc, will be equal to center of mass speed, V center of mass, minus omega r, due to the fact that we have a rotation motion here. So this would cause omega r, tangential velocity, and we already have a V center of mass equals omega r that's pointing up. So the contact point has a zero speed. Therefore, since the contact point doesn't slip here, we have static friction. Okay. Now, if I write Newton's second law, the net force on the y-axis must be equal to mass times the acceleration on the y-axis. As you can see, we have the normal force pointing in plus j hat direction and mg cosine beta pointing in minus j hat direction. So we have the normal force minus mg sine beta, and under the influence of these forces there is no motion on the y-axis, so this must be equal to 0. The net force on the x-axis is basically now we have the component of mg here pointing down, minus mg sine beta I hat plus fs I hat. So we have two contributions. One contribution from the component of the weight on the x-axis, mg sine beta, and minus the static friction Fs is equal to mass times the center of mass acceleration. So I'm assuming that the acceleration, center of mass acceleration, would be pointing down. Okay, so once again, the argument for the static friction, Fs must be directed up the hill to result in a torque So we determine the direction of the torque by pointing from the pivot point, the center of mass, towards the application point of the force, curl our fingers towards Fs, and we find that the thumb points in k hat direction. So this gives us k hat direction. So this torque will lead to the direction for the center of mass acceleration in minus I hat direction, because it's trying to slow down the rotation. So we will see the angular speed omega must be decreasing as it rolls up. So from energy arguments, we can also see this. We have an increasing potential energy. That means we should have a decrease in the rotational kinetic energy and the translational kinetic energy of this ball. So we will have a decrease in omega as it rolls up. So this can be provided by the torque caused by static friction, and the net acceleration we will have here, mg sine beta minus fs, will be in minus I hat direction. Okay, so part B. What is the acceleration of the center of mass of the ball? Now, if I write the torque, the net torque acting on the ball, it's due to the static friction. As I said, it's in plus k hat direction. So r cross fs, so rfs, because they're perpendicular, in k hat direction will be equal to the moment of inertia, I center of mass, times alpha, the angular acceleration. So if we multiply the left side and right side with f, so we will have r square fs k hat is equal to, or let's just look at the magnitudes here. R square fs is equal to I center of mass alpha times r, and the acceleration of the center of mass is related to the angular acceleration as alpha times r. So r square static friction must be equal to I center of mass times acceleration of the center of mass. So we see that the static friction magnitude must be equal to I center of mass divided by r square times acceleration of the center of mass. Now, if I look at the x component equation from Newton's second law, I can substitute for fs ia over r square. So mg sine beta pointing downhill minus the static friction pointing uphill, I center of mass, acceleration of the center of mass, divided by r square, must be equal to mass times acceleration of the center of mass downhill. So we can isolate acceleration of the center of mass. So we will have I center of mass divided by r square plus capital M. So I'm collecting all the terms on the left hand side here. So this goes to the left hand side, and multiplied by acceleration of the center of mass is equal to mg sine beta. So we have isolated the acceleration of the center of mass. Now the question is, what is the moment of inertia for rotations about the center of a uniform sphere? And this we have done in problem 10.24. It was 2/5 capital M r squared. So if we substitute that here, 2/5 capital M r squared, so we have I center of mass, divided by r squared. We can divide this by r squared plus capital M times acceleration of the center of mass is equal to mg sine beta. So these r squares will disappear. We will be left with 7/5 capital M acceleration of the center of mass is equal to mg sine beta. Now we can see that we don't need m cancels. And acceleration of the center of mass magnitude-wise is equal to 5g divided by 7 sine beta. Direction-wise, it's in minus I hat direction. Okay. So what we see is that the ball decelerates while rolling up the hill. So the ball decelerates while rolling up the hill. Okay, let's look at part C. Part C is asking the minimum coefficient of static friction to prevent slipping. Now we have the static friction force Fs given by I center of mass, A center of mass divided by r squared. And for I center of mass we can substitute 2/5 mr squared, so r squareds cancel, we have 2/5 m times acceleration of the center of mass is 5g/7 sine beta. Therefore, this becomes, because the 5's will cancel, 2mg sine beta divided by 7. And on the other hand, what is the normal force acting on this system? Normal force is equal to, here is a mistake, it should be mg cosine beta, right? So you can see the component on the y-axis is mg cosine beta, the component on the x-axis is mg sine beta. So the normal force must be equal to mg cosine beta. So normal force must be equal to mg cosine beta. And we know that the static friction force is less or equal to coefficient of static friction times the normal force. So it is less or equal to coefficient of static friction times mg cosine beta. Now, the static friction force we have calculated to be 2 mg sine beta divided by 7. This should be less or equal to mu s times mg cosine beta. So these m's will disappear. So we find that also the g's will disappear, right? We have too many g's. 2 over 7 sine beta, if we take this cosine beta at the bottom here, it becomes tangent beta. So 2 over 7 tangent beta would be less or equal to mu s. So this gives us the minimum coefficient of static friction to prevent a slipping to be 2 over 7 tangent beta. Okay, so we can summarize what we did here. We have a ball that is rolling without slipping up a ramp. So it's gaining potential energy, therefore it must be losing rotational kinetic energy and translational kinetic energy. So this is going to have omega in the clockwise sense. Now this is treated as a uniform solid sphere. What is the direction of static friction on the surface? It's either pointing, it's always parallel to the surface, it's either pointing downward or upward. We will determine using the free body diagram what is the acceleration of the center of mass and what is the minimum coefficient of static friction. Now, in the free body diagram, we have the weight pointing from the center down, making an angle beta with the normal axis. So it has a component mg cosine beta on the normal axis, mg sine beta on the x-axis. And the static friction must point in such a way that this angular speed will be decreasing in time. So we need a torque r cross fs that will be causing a decrease in omega, causing an angular acceleration in the basically opposite direction. So for rolling without slipping, we know that the center of mass speed is equal to omega times r, angular speed times the radius r. The contact point should have zero velocity. It is v center of mass minus omega r. So minus omega r points in the minus I hat direction and v center of mass points in plus I hat direction. We have zero contact point speed, therefore we have static friction. The net force on the y-axis is normal force minus mg cosine beta. Net force on the x-axis is mg sine beta minus fs, assuming acceleration is pointing downward. And we have determined the direction of static friction by the requirement that angular speed must be decreasing in time. So the torque provided by the static friction r cross fs is in k hat direction using the right hand rule, which is equal to, according to Newton's second law rotational form, I alpha. If I multiply both sides with r, acceleration of the center of mass is alpha r, so that's derivative of omega r with respect to time. And r square fs is I center of mass, a center of mass, so we can substitute for static friction IA over r square in the x equation. So we can isolate the center of mass acceleration in this equation. And by noting that the moment of inertia of a uniform sphere for rotations about the center is 2 over 5 mr square, we can determine the magnitude of this acceleration, 5g over 7 sine beta, and since we assumed it's pointing downward here in writing this equation, it's in minus I hat direction. And the static friction we can calculate by substituting this result in IA over r squared, and I is 2 over 5 mr squared, and this should be less or equal to coefficient of static friction times the normal force and where the normal force is mg cosine beta. So this gives us our requirement that μs should be greater or equal to 2/7 tangent beta, giving us a minimum value 2/7 tangent beta.